I k partial q, say I xi plus gamma I jk, the Christoffel symbols, xi, yj, and this is the k component, so this is partial qk. So we can do derivatives intrinsically on the manifold, and this allowed us to say, what do we mean by parallel? What is parallel? How can you say this vector is parallel on that vector on the manifold? We can decide that in the ambient space, but how you can do it on the manifold? So you can do it using this covariant derivative, and actually this was the start. It wasn't like, okay, we need a derivative like I discussed last time, and then we can decide the parallelism. It was the other way around. Lec12 wanted to define what do you mean by a parallel transport. And from there he came up with a connection. And this seminal paper actually, it's remarkable. In this, it's actually never been translated to any other language, but there are papers that talk about it. In this paper, to come at the parallel transport, or the definition of a parallel manifold, which started all this, based on which the general relativity and almost everything, he made use of principle of visual work. So the notion of parallelism in the middle of the proof, he used an argument from the principle of visual work. It's very, very interesting. But anyway, so he trained as a mechanics person, analytical mechanics person from that school. So yeah, we define what we mean by parallel, and more importantly for us here, we define what we mean by acceleration of a curve. Which is not like gamma prime. Gamma prime is the derivative of the velocity vector along the curve, and from which we can define the geodesic, the straight line. What do you mean by a straight line on a curved space? It's a curve with zero acceleration. So nabla gamma prime is zero, and this equation we can write it in coordinates as a second order differential equation. This is what we did last time. If you have any question, please stop me. And then we talked about Romanian metric. So it's a map that takes a point and gives you just a positive definite and symmetric matrix. So in other words, GP acts on vectors in the tangent space, takes a vector, another vector, do the dot product between them and gives you a real number, right? So GP, when acts on two vectors, it's simply Gij, Vi, Wj, or if you write it in our usual way, it's a row times the matrix times a column W, okay? The result is a real number. It represents the dot product between the two vectors in the tangent space. Using this tool, we defined last time the length of a curve, which is the integral over the interval of the curve, the norm of the velocity vector. The norm from the dot product is the square root of the thing dot product with itself. So G gamma of t of gamma prime of t, gamma prime of t. And we have dt. So this is the length of the curve, from which we defined what do we mean by the distance. We can now measure distance between points on the manifold. So distance between 2 points P1 and P2 is the minimum or the infimum between all of these curves, the length of all these curves connecting the 2 points. So the infimum of all the length is of gamma, such that gamma takes 0, 1 to the manifold, and gamma of 0 is the first point, gamma of 1 is the second point. This is equivalent to minimization of L of gamma, which is the integral of G, Ij, we have a square root here, Gij qi dot qj dot dt, right? And last time we said, well, we better do it with the energy instead, so we don't have this square root. The resulting curve is the geodesic, the straight line, the shortest path.
Professor,
Yes.
are these two optimization problems exactly the same? Like,
They are equivalent, but actually, I mean, there are technical details that I skipped for calculus information. Minimization of this guy alone with the square root is not well posed. You need to add a constraint, which is constant speed. So minimization of L with constant speed is exactly equivalent to minimization of E. But the latter problem, which is minimization of E, is a convex problem, so it's easier to solve without a constraint. You get the constant speed as a byproduct. So I just skipped these details. Okay, so this was actually last lecture. And today we will continue upon that. So let's continue with the definition of L. Let's recall L from here, please. Let's recall L. So L of gamma is the integral of Gij square root. Gij. I have Q dot and Q dot. So it's Q, dq by dt, dq by dt. I can get this dt squared outside of the square root, it would be dt. So I would have just here dqi, dqj, right? So this is the length of gamma. Any question about that? Any question about that? Okay, and by definition, for a length over a curve, it's the integral of the element length, correct? So now I can combine these two guys. From this equality, you get that the ds squared is gij dqi dqj. So the Riemannian metric gives you a formula for your length element. Obviously, because we said the Riemannian metric is a metric. We use it to measure distance. So it gives you a way to write an expression for your element length, so that when you integrate, you get the distance. So if you can write your element length, vice versa, if you can write your element length as differential in your coordinates, then you can extract out the Riemannian metric. And this is what we're going to do now on an example for S2. This lecture is quite similar to the last lecture in 241, but with a bit more details. So we have here example in S2. This is X, this is Y, and this is Z. Your sphere. So this is a point on the sphere P. So we have this angle is theta, this angle is phi, as we said before, and we can write the coordinates. We can write x, y, z. So it would be confusing. I'll write sphere because we're gonna write s squared. So sphere, on the sphere we have x, y, and z from the ambient space is using these two coordinates. I have two coordinates on the sphere, but now I'm writing 3 because I'm in the ambient space. In terms of these two coordinates, it's cosine theta, cosine phi, what is that? Sine theta, cosine phi, and negative sine phi, right? And then I write my element length in the ambient space. This is already known because I'm in a Euclidean space. It's dx squared plus dy squared plus dz squared. This is easy because I can write dx from here. This is x, so dx is negative sine theta cosine phi d theta, and negative cosine theta sine phi d phi, and so on. So this guy, for example, is what? Negative cosine phi d phi, right? So this is dx squared plus dy squared plus dz squared. Okay? Any question about that? And you add them together. So you get ds squared is just, make all the cancellations. You get something like cosine squared phi d theta squared plus d phi squared, I guess, yeah. So this is your element length on the manifold coming from the ambient space, induced by the ambient space. So I can actually extract my Riemannian metric here, because if I have my element length, I can write it on this form. It's like a row matrix, a column, then your matrix is the Riemannian metric. So this is d theta and d phi, d theta and d phi, and please fill the Riemannian metric, right? So you just cosine squared phi, 0, 0, and 1. This is your G. Any question about that? I mean, we did it in 241, but if you didn't take it or you have any question, please feel free. Because you gotta do it in the homework, in the final, several places. If you have any surface, can you get your Riemannian metric from the ambient space or not? Any question? Okay, so that's fair enough. We got our Riemannian metric.
Professor?
Yes,
We did it using the ambient space.
we did here
Okay.
in the black line. ds squared equals dx squared y squared z squared, right?
So is there a way to do it solely on the manifold?
To derive it
Yeah.
on the manifold? No.
The other way around is to find the Christopher sum.
No, the Christopher sum is much harder actually. And you need to do it also from the ambient space. The thing of differential geometry is that, okay, you get an element from the ambient space, but then you work with this guy on. So this guy allows you to do dot product on the manifold now on. So whenever I want to do dot product, I will not go back and do it in the ambient space and project. It's already done here. This carries all the information. And the same for the Christopher symbols. So here I also can define my energy of the curve, right? It's simply the integral of, remember this, the energy of the curve. You can define it as Gij dqi dqj, or with the dots and dt. We prefer with the dots and dt, so I'll carry this over as cosine squared phi theta dot squared plus phi dot squared dt. And we want to minimize this guy, subject to no constraints, so this is your Lagrangian, right? So you have d by dt partial L partial theta dot minus partial L partial theta is 0. This gives you whatever we get. What do we get? So we get something like cosine squared phi theta dot. So this is cosine squared phi theta double dot minus 2 cosine phi sine phi theta dot phi dot equals 0. And the other equation, you don't need to write. Partial phi is 0. Here is a bit easier. It's phi double dot plus sine cosine theta dot square. So the first equation, if you divide by cosine phi, so this goes away, and this becomes tan. Then these equations are exactly similar as the ones that we wrote last time using this guy. We're geodesic, right? First, what are the red equation? What does the red equation represent? What does this red equation represent? What does it represent?
Partial movements here. What the equation is a function of partial movements.
No, I mean you're jumping. What does it represent from here? What does it represent?
Minimum distance.
Yes, so we started with the Riemannian metric, and I'm getting the geodesic of the Riemannian metric. The red equation represents the geodesic of the Riemannian metric, the shortest distance from the point of view, the straight line from the point of view, shortest distance, right? This is the shortest distance. This is the red equation exactly. This is how we derived it. Okay, the black equation here, nabla gamma prime, this is a geodesic from another perspective. That is a zero acceleration that we derived last time just from the knowledge of nabla. equivalently from the knowledge of the gammas, right? Gamma theta, for example, was negative tan phi and negative tan phi. And they are exactly equivalent. They are exactly equivalent. In particular, if you know from the beginning that they are exactly equivalent, you could have used this tool, because it's very easy to get the Riemannian metric. You can use this tool to get the gammas. I highly encourage you to get one of these gammas like this, negative tan phi, for example. Get it on your own without the tools that I said here. So I didn't tell you how to get gammas last time, right? So, but I gave you the definition. Like this guy, for example, this tan phi, when you write, this is E theta and E phi. So get a unit vector in the E phi direction, unit vector in the E theta direction in the ambient freedom space. Do the direction derivative in the ambient space, you will get a vector, project it on the sphere. So you will get a vector in the tangent space on the sphere that is something in the E theta and something in the E phi, right? This something is gamma theta phi theta gamma theta phi phi. This guy is that. So try to do this. It took for me like, I don't know, I'm very bad at computation, but it took like one page and a half or 2 pages to arrive at this guy just from this whole dilemma. It's quite hard. I mean, it's cumbersome. Actually, this was the main motivation why Lec12 did this seminal work. The main objective wanted to minimize the computation or reduce the burden of the computation to get the Christoffel symbols. More importantly, not the Christoffel symbols per se, but the curvature of the Riemannian method. So we will see how to get them in an easier way. But if you know a priori that such an equivalence exists, that if this equation, how do you write this equation? Well, this equation is qk double dot plus gamma I j k qi dot qj dot is 0. So in particular for theta, for example, for theta, this will be theta double dot plus theta dot phi dot some matrix, I don't know, theta dot phi dot equals 0. And because I know the equations of motion from the red thing, I can fill out my matrix here, right? From the first line, I can fill my matrix. It's theta double dot, that's okay, taken care of. And I have negative 2 tan phi, theta dot phi dot. So this here, negative tan phi here, and negative tan phi here. So this is gamma theta, okay? And you can do the same from the other equation. Any questions so far? If we know such an equivalence exists from the beginning.